Hey everyone. Last time we were working on the special case of applying the fundamental theorem, and that special case was when the order of our group was a power of a single prime. Now what we want to do is move on to the general case. And so what would that mean then? Well, the general case would follow the situation where if we have an integer m as the order of our group here, so right, just to remind you, right, we're talking about the order of G. It's a finite abelian group of order m, and now what we want to do is say that the m is a power of some collection of primes p1 to the n1 dot 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 up through p sub k raised to the nk, right? So we know, according to the fundamental theorem of arithmetic, every integer can be expressed, every integer greater than 1 can be expressed as a product of primes in essentially a unique way, right? Up to ordering of the primes, right? This expression is unique. And so then that would mean that this would cover every possible order, right? Every order of every finite abelian group is going to be of this form, right? So now, according to the fundamental theorem then, so in this case, G is isomorphic to, we'll say, I want to say that, G1 cross, let's call it like that, G2 cross dot 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 cross G sub K, where G is an abelian group of order P, I guess I need to say G sub I, so we're G sub I, right, where each one of these G sub I, so each Gi, that looks kind of weird there, where each G sub I is an abelian group of order P sub I raised to the N sub I. And I think I got all my subscripts and superscripts correct here. So the idea is, if you have a finite abelian group, it is going to break up into a bunch of, it's going to break up into a product of abelian groups, where each one of those abelian groups falls under our special case. So we can now apply the special case to each of the GIs, and then we'll just sort of mix and match to get all the possibilities for who G could be isomorphic to. So in the end, what we'll be able to do is we'll be able to write down a list of all possible products of cyclic groups, so that G must be isomorphic to one of those cyclic, or one of those products of cyclic groups on our list. So now we'll say apply the special case to each G sub I. So that's the process. So let's do an example here. What I'd like to do is classify the abelian groups of order 1176, so 1176, which has prime factorization 2 to the third times 3 times 7 squared. So here's the idea. According to this process right here, what we know is that any group of order 1176 is going to break up as a product, in this case, of 3 abelian groups, a G1, a G2, and a G3, where the first one has order 8, the next one has order 3, and the last one has order 49. So here's the solution then. If the order, all right, so if G is abelian and the order of G equals 1176, then G is isomorphic to G1 cross G2 cross G3, where order of G1 equals 8. The order of G2 equals 3, and the order of G3 equals 49. And so what we want to do then is write down the choices, the possibilities for each of these three G's right here. So the possibilities for, and then we have, first we'll do G1. So let's see, G1 is an abelian group of order 8. And so what do? 8 is 2 to the third, so we want to look at the possible partitions of 3, right? And those are 1 plus 1 plus 1, 1 plus 2, and 3. So the possibilities for G1 are going to be Z cross Z cross, not Z, we have Z squared, Z2. Z2 cross Z2 cross Z2, Z2 cross Z4, and Z8. For G2, well, let's see, G2 has order 3. The only group of order 3 is Z3. And then the possibilities for G3, well, let's see, so G3 has order 7 squared, so the partitions of 2 are 1 plus 1 and 2, and so it could be Z7 cross Z7, and it could be Z49. So now, what we would like to do is write down a list of all possible groups, all possible abelian groups of order 1176, and that way we'll know that G must be isomorphic to one of the groups on that list. And the way we do that is we start taking combinations of possibilities for G1, G2, and G3, write down all the different combinations. That is our list. That's our classification of abelian groups of order 1176. So G must be isomorphic to one of the following. Okay, so it could be, and we want to just kind of be systematic about this, so Z2 cross Z2 cross Z2. There's one choice for G1. Cross Z3 cross Z7 cross Z7. It could be Z2 cross Z2 cross Z2 cross Z3, and now I'm going to switch out that last one there, so cross Z47. It could be Z2 cross Z4 cross Z3 cross Z7 cross Z7. It could be Z2 cross Z4 cross Z3 cross Z49. So notice what I'm doing. I'm keeping the first group the same. The middle one, right, is going to be the same all the way through. Right, the Z3 will always be there, and then I'm just alternating the choices for the last one. And so now the last possibility, or the last two possibilities, will be Z8 cross Z3 cross Z7 cross Z7, and Z8 cross Z3 cross Z49. So what we have now is a list of 1, 2, 3, 4, 5, 6 groups. Every abelian group of order 1176 must be isomorphic to one of these on the list, and these are all non-isomorphic groups. Right? So there are exactly 6 abelian, up to isomorphism, exactly 6 abelian groups of order 1176. All right, so here's the idea in applying the fundamental theorem to classify abelian groups. Now, I'd like to do another example. And this is similar to one of the examples, I guess it would have been the last example that I did. Remember I made that table and I wrote down, it was like element and orders, and we had this strange collection of numbers that were, you know, somewhere between 1 and 64, I think it was. So this is kind of telling you, I just kind of mysteriously pulled these numbers out and said, hey, it turns out that this is a group. Here's where this came from. So for n greater than or equal to 2, let u sub n be the set of positive integers that are less than n, so less than n and relatively prime to n. So for example, U6, right? Who's that going to be? Well, U6, that's going to be the numbers, positive integers less than 6, relatively prime to 6. And so we would just go through the list. Well, okay, so there's 1, of course. 2, no. 3, no. 4, no. 5, yes. And so that's U6. If I did U sub 9, 1 is always going to be in U sub n. And then 2 is relatively prime, 3 is not, 4, 5, 6 is not, 7, and 8. All right, so there's U sub 9. So there's the idea. Let me just do one more. So U sub 20. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 is in there. 10, no. 11, 12, no. 13, yes. 14, no. 15, no. 16, no. 17, yes. 18, no. 19. Okay, so there's U sub 20. Now, under... And so, by the way, what we were looking at in that last example I did, I think there were 16 elements in the group. That was U sub 65. What we had was the list of numbers that were less than 65 and relatively prime to 65. So, under the operation of multiplication, mod n, UN is an abelian group. And I believe, if I remember correctly, this is on your next homework. It asks you to actually prove this. Now, here's the here's what you'll need for this. So, of course, associativity is automatic. So let's say here's the idea. So associativity follows from, well, this is really from multiplication of real numbers, I guess you could say. So associativity follows from associativity of multiplication of real numbers. For the identity, 1 is definitely the identity. One is the identity. And then for inverses, well, I'll just call this is really what you need to do. So exercise, show that if we have A in UN, then there exists a B in UN such that A times B is equal to, or is congruent to 1 mod n, right? There exists an inverse. And here's a hint, I guess we could. So what you'll need is the definition of the GCD. So use the definition of GCD, and by that I mean the one that we gave in class, not the one that you learned in number theory, but as the generator, the least positive generator, or the positive generator of the group generated by AM plus BN. All right, so use definition of GCD, and what else do you need? I think you need the division algorithm, yeah, and the division algorithm. So that would be the steps to verify it as a group. Of course, I guess, and I kind of glossed over this. Closure. Right? If you take two elements in U sub n, well, both of them are relatively prime to n, which means that they have no common factors with n. So if you multiply two things that have no common factors with n, you're not going to create a common factor with n, right? So that's where the closure part comes from. Now, now that we know who this is, what I'd like to do, and then now that we have the full knowledge of applying the fundamental theorem, let's do an example here. So let's express, I guess we're still doing an example really, so let's express U of 21, which is 1, 2, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 15's in there, 15, 16, 17, 18 is not, 19 is in there, and 20 is in there. So what I'd like to do is express this group as a product of cyclic groups. And when I say as a product, meaning it's isomorphic to the product of cyclic groups that we're going to write down here. So let's see what the order is here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I screwed something up, didn't I? It's not 13. Oh, 15 is not in the list. That's my mistake there. Okay, so whoops. Back up. 15 should be gone. 16, 17, 19, and 20. When I heard the number 13, I knew that couldn't have been an example that I would want to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Okay, so the order of U21 is 12, which is 2 squared times 3. So what do we do? Well, for the factor of 2, right? So that means, let's write it out the way we did before. So U21 has to be isomorphic to G1 cross G2, where the order of G1 equals 4 and the order of G2 equals 3. Well, there are two abelian groups of order 4, right? So for the G1 part, it's going to be Z2 cross Z2 or Z4, and the G2 part is going to be just Z3, right? So what we know is that U21 is isomorphic to, and our possibilities are Z2 cross Z2 cross Z3 or Z4 cross Z3. By the way, notice because 4 and 3 are relatively prime, this group right here is isomorphic to Z12. It's cyclic, right? So we could say that either it's cyclic or it's not. And how would we decide this? Well, one way to decide is to check the orders of the elements within this list right here. If we find an element of order 12, then it's got to be isomorphic to this one. If not, it's got to be isomorphic to this one. So, and I'm just going to do the same thing. I'm going to make a table. I computed the orders of the elements already, and so I'll just write those down. But you know, so here we go. 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, and 20. And so now, right below, I'll write what their orders are. So, of course, 1 has order 1. And then it's going to go 6, 3, 6, 6, 3, 6, 2, 6, 6, 2, 3, 6, and then 6, 2. Right, so each and one of you could actually compute this out. What do? You just start raising the number to various powers, and then reduce mod 21. So if you compute 2 to the first, second, third, fourth, and fifth, it will not be congruent to 1 mod 21, but 2 to the sixth, what's 2 to the sixth? It is 64, right, which is congruent to 1 mod 21. So that's the idea. Do that for each one of these, right? As soon as you get something that's congruent to 1 mod 21, you can stop. Well, okay, I don't see anything of order 12 on this list, so we are guaranteed then that U21 is isomorphic to that one. Right, so since we have no element of order 12, we see that U21 is isomorphic to Z2 cross Z2 cross Z3. There's a corollary to the fundamental theorem with the proof that actually takes a little bit of work. So this is going to be corollary 11.6. Really? Do we have that many theorems already? Yeah, I guess we've been studying direct products for a little while, huh? Yeah, okay. Yeah, it seemed like more theorems are than I realized. But okay, so corollary 11.6, and it goes like this: if G is a finite abelian group, and M, we'll say M in N, divides the order of G, then G has a subgroup of order M. Now, we already know this. We already know this for cyclic groups, right? For every divisor, we have exactly one subgroup of a given order, or of that divisor's number, the order of, how do I say that right? For every divisor of the order of a cyclic group, there is exactly one subgroup corresponding to that divisor, meaning it has order equal to that divisor. So, okay, there's actually something to prove. So, according to the fundamental theorem, we have a way to write G. It's isomorphic to, so by the fundamental theorem, G isomorphic to zp1 to the n1 cross dot 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 cross z p sub k to the n sub k. Right, for some primes p, p sub I, so for some primes p sub I and exponents n sub I. So we'd say and natural numbers, or yeah, and n sub I in n. So now, yeah, where, by the way, and I guess I should say, where the order of G is equal to, so let's see, what is the order of G? It's p to the 1 times n1 plus dot, or times p1 n1 dot 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 p k to the nk. So, okay, now, if m is a divisor of the order of G, then we know the form that it's got to take. All right, so it follows that m is going to look like what? Well, it's going to look like a product of powers of these exact same primes, but with potentially different exponents, right? Likely different exponents. So m is going to be p1 to the, what do I use here? S1 p2 to the s2 dot 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 p k to the sk, where each of these s's is somewhere between 0 and the corresponding n, right? Okay, now we're just going to construct this group now. So in z, okay, so we're going to work in z sub pi to the n sub I. The element p sub I raised to the ni minus si, right? So there is, this is an integer between 0 and pi raised to the ni. Right? So that number right there generates a subgroup of order. So remember how to compute the order, right? So it's going to be so the order of pi ni minus si is equal to p sub I to the n over GCD of p sub I n I minus si, comma, p sub I to the n sub I. The GCD is going to be p sub I to the ni minus si. So this is pi to the ni over pi to the ni minus si. And then when we subtract the exponents, this is p sub I to the si. Yep. So in each of the factors for G, we have a subgroup whose order is p to the I si. And it's a cyclic subgroup, right? Generated by that element right here. So now, the subgroup And I'm going to write it like this. P1 cyclic subgroup generated by P1 to the N1 minus S1. All right, that's living in Z sub P1 raised to the N1. And then you just go down the list here. P2, N2 minus S2 cross dot 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 cross P sub K to the NK minus SK. This is the desired subgroup. Is the desired subgroup. All right, so it's essentially rigged to work. It's a bit of a messy computation, I guess, but I mean, we're just using that formula from chapter 6. I think this is formula 6.7, or for theorem 6.7. So, anyways, there it is. I want to end this chapter with one more theorem, and this theorem, once again, I'm just going to state this theorem. It's actually subsumes our fundamental theorem, and this one, so goes like this. So theorem 11.7 is called the fundamental theorem of finitely generated abelian groups. So instead of just finite, now we have finitely generated, which means it has a generating set consisting of a finite number of elements. And it goes like this. So if G is finitely generated and abelian, then G is isomorphic to Z P1 to the N1. Am I going to use the cross cross Z P sub K to the N sub K cross Z cross Z cross dot 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 cross Z. So if you have a finitely generated abelian group, which means that is actually infinite, right? Then it's going to have sort of, you can think of it as a finite part and an infinite part, right? It's going to look like a finite abelian group cross some collection, some number of z's, right? Some collection of integers, where the pi to the ni k and the number of factors of z are uniquely determined by G. One more X there. So a finitely generated abelian group has what you can think of as a finite part and an infinite part. The finite part follows the formula for the fundamental theorem of finite abelian groups, and then you tack on this collection of z's, that's the infinite part. So every finitely generated abelian group looks like this, or is isomorphic to a group of this form. And so that is a good place to stop. We are definitely not going to prove this theorem. It's even more difficult than the previous one. So, all right, we'll see you next time.